So let's start today's lecture. In the last class, we have discussed about the PLA, programmable logic array, and the structures was like this when we have solved an example and implement the Boolean function with the help of PLA. So in the PLA, we have programmable AND array and programmable OR array. This is your AND array, which is programmable, and this is your OR array, means both arrays are programmable. Now in today's class, we are going to discuss the PAL, programmable array logic. The structure is almost a bit same as PLA. In PAL, PL is a programmable logic device with fixed OR array, means the connections in the OR gates are fixed and a AND array is programmable. So as distinct from the PLA, in PLA both AND and OR arrays were programmable, but in case of PAL, our OR array, that is the output array, is fixed and we have a programmable AND array. And the structure of the PAL is like this. You can see that in this particular example we have four inputs, I1, I2, I3 and I4, and with these four inputs we have 8 inputs line, I1, I1 naught, I2, I2 naught, I3, I3 naught, I4 and I4 naught. The major difference between PLA and PAL is like this. We have 2 extra inputs line, and these inputs lines are nothing but F1 and F1 bar. So the first output of the OR gate is fed back as the input, and we have to design, or we have to find out the optimal Boolean function in such a way that we can minimize the number of minterms. Because when OR array is fixed, so we can say that this particular output F1, F2 or F3 and F4, we have 4 outputs and each output has 3 minterms only, because each output has 3 AND gates. So the OR array is fixed, it will combine only 3 inputs or 3 minterms, and the minterms may vary. So let us discuss it with an example. Suppose now when addressing with a PAL, the Boolean functions must be simplified to fit into each section. Unlike the PLA, a product term cannot be shared among 2 or more gates. Therefore, each function can be simplified by itself without regard to common product term. So the product term we have to implement, or we have to burn each for each output, because the OR array is programmable. OR array is fixed. Now the output terminals are sometimes driven by tri-state buffer or inverters, as in case of PLA. Suppose take an example. We have 4 inputs, W, X, Y and Z. We have 4 functions, W, X, Y, Z, and W is summation 2, 12, 13. These are the minterms. X has 7, 8, 9, 10, 11, 12, 13, 14, 15. Similarly, Y equals to summation Y equals to summation 0, 2, 3, 4, 5, 6, 7, 8, 10, 15, 11 and 15, and Z is 1, 2, 8, 12 and 13. So what we have to do first we have to solve all the minterms with the help of K-map or tabulation method, so that we can find out an optimal minterms. So simplifying the 4 functions as W comes A, B, C bar plus A bar, B bar, C, D bar, and this is this is obtained after solving with the help of the K-map. So as a practice, you can solve it with the help of the K-map. So after solving or minimizing, it comes to be W equals to A, B, C bar plus A bar, B bar, C, D bar. X is A plus B, C, D. Y is A bar B plus C, D plus B bar D bar, and Z equals to A B C bar plus A bar B bar C D bar plus A C bar D bar plus A bar B bar C bar D. So you can see that we have further minimized this because W equals to A B C bar. A B C bar is the first term. A bar B bar C D bar. So A bar B bar C D bar. So these two terms can be minimized as W, because you can see in the last example or the structure that we have here, we have the two another inputs, that is F1 and F1 bar. So here in the case we have implemented with the help of W. So in the last expression for the Z, we have combined first two terms as W and the rest two terms are same. So you can see that in each OR term we have maximum of three product terms. Here is 1, 2, 3. Here is 1 and 2, 2, again 1, 2, 3. So we can use an a PAL like this, which combines three product terms. PLA and PL are both available in the market, and they have certain number of inputs and certain number of outputs. So whenever we are implementing a Boolean function, we have to choose the which type of which size of PLA is required for our implementation. Now we again, as in case of PLA, we have to construct a PAL programming table. Here in the last expression, we have seen the Z has 4 product terms, and we can replace by W with 2 product terms. This will reduce the number of terms for Z from 4 to the 3. So in the same manner, we have constructed a PAL programming table. In the first, W has A, B, C bar, and A bar, B bar, C, D. These are the terms in the W. So we have put it first for the first AND gate. A is represented by 1, B represented by 1, C bar represented by C dash. In the second term, A bar, B bar, C, D bar. And the third term has been kept open because we are not doing any connection. Similarly, for again, we have taken 4 inputs A, B, C, D, and W. In the second, x equals to A, all are don't care, and next term is B, C, D. So dash 1, 1, 1, dash, W is not included again here. In the next, for the expression of Y, we have 3 min terms. So first is A bar B, C, D plus B bar, D bar. So we have put it where there is a complement, we have put it 0. Where there is a true value, we have put it 1. And the rest of the terms are don't care or open circuited. Again, Z has again 3 terms. So the first term is W. If it is W bar, then we have put it here 0. Next term is A, C bar, D bar. So 1 dash 0, 0 dash. Next is A bar, B bar, C bar, D. So 0, 0, 0, 1 and dash. So this is the way how we construct a programming table for PAL. So you can see directly that here, except the W, we haven't taken any min term which is repeating simultaneously or more than one time, as it was not in the case of PLA, because in PLA we can use min term many times, but in case of the PAL, each min term is there was some network issue. Now come to the fuse burning. Just in case of, we can again look at the table. So this is your table. Where there is a connection, we have to put cross, and otherwise we have to left open circuited. Now comes to the PLA table, we have inputs A bar, B bar, C bar, D bar, and W bar. So where there is a connection, we have to put a dot or a cross at that line, because we need not to program the OR array, because OR array is fixed and we can see directly that in the first term and the second term for the W and X, we have only two minterms. So these two gates are not used. All fuse intact, that is always equals to 0. So this is the way, the first term we can see that A, B, C bar. So we have put it cross, and the second term is A bar, B bar, C, and D bar. So you can see the Z, we have W, the first term, second term is A, C bar, D bar, and the next term is A bar, B bar, C bar, and D. So this is the way how circuit is implemented. But when it comes to be in the examination, you may leave at the after completing the programmable table. So first you will be given the Boolean functions. The Boolean function is minimized with the help of K-map. Then with the help of the after implementing after solving for the K-map, we have to if we look that further we can minimize the minterms, because the number of terms are limited for each OR array. Then we have to make the programmable table, programming table, and that's enough. We need not to construct, or we need not to draw the circuit diagram. So the next topic, we are starting unit 2, that is digital logic families. In this we are going to discuss all type of logic families available. You need not to bother about the circuit diagrams, because there will be a comparative characteristic comparison, and that is always asked in the examination. Compare the different characteristics of different logic families. So here we are going to discuss what type of the logic families are available and its evolution, and which logic family is performing performing better in which way, and what are the comparison between their characteristics. So let's discuss. Let's start with the overview. So first we have integration. How are the technologies are there? Moore's law, DTL, diode logic, RTL, transistor logic, TTL, transistor logic, and the different logic families in the TTL, ECL, emitter coupled logic, CMOS family and its evolution, and we have a final in the final will summarize the overall overview of the logic families. Now let's come to the integration level. We have different types of technologies, and the first is SSI, small scale integration, which has less than 12 gates per IC. Chip here is the IC. Then MSI, medium scale integration, where we have about 10 gates per chip. Then LSI, around 1000 gates per chip. Then we have VLSI, about 10,000 gates per chip. We have further ULSI, ultra large scale integration, where we have 100,000 gates on a IC. GSI, the gigantic large scale integration, in which we have around 1 mega gates per IC. So these are the ICs looks like. So you can say that you are using VLSI in your microprocessor in your PC or in your laptop. That is constructed under VLSI, very large scale integrated circuits. So this is how an IC looks like. We have different types of pins. We have black color of coding, and inside that, if we are using VLSI, then there are 10,000 gates on a single IC. Now come to the evolution. As predicted by Moore, a co-founder of the Intel in 1965, and it predicted, and that is known as the Moore's law of integration, that a number of transistors to double every 1.5 year. That is, after every 18 months, the number of transistors on an IC will be doubled. So you can see in the current scenario, when you are when you are buying a latest mobile phone in today, then you will see that after half an year, you will see that there will be a new mobile with the same range, with more features in the market. That means the mobile phone or the digital IC you have purchased 1.5 year back, that has been obsoleted, and the new technology with new more features is available in the market, and that is because of the Moore's law. And we can see it with the help of the graph. Then in 1971 there was 4004 transistors on a IC. These are the number of transistors. You can see in the Pentium 3 there are about 100 million transistors on a processor. So this is the evolution. We have started with the 4,000 gates or 4,000 transistors, and now we are using 100,000 transistors on a IC. Again, now your processor is IC. So this is the evolution of the technology. And in the digital world, you will see that after every 1 or 2 years, there are new technology, new features on your mobile phone, new features on your processor. We are getting i3, then i5, then i7, now currently i9, and we are working on i11, and that is only due to the Moore's law. Now come to the typical logic device pins out. These are the ICs. When you will be in the lab, you will use these ICs. So first is the hex inverter. You will see such type of IC which have 14 pins. Here you will see a cut, and in each IC, when you will see the top, there will be a black circle. There will be circle. Now where there is a circle, this is the pin number 1. Then you move pin number 1, 2, 3, 4, 5, 6, 7. Then 8, 9, 10, 11, 14, 15. Sorry, 8, 9, 10, 11, 12, 13, 14. So all of the ICs you are using in the lab are of 14 pins, and pin number 7 of all IC is ground, that is 0, and pin number 14 of all IC is VCC, that is your power supply. You will be well aware with the VCC and ground when you have studied in the basic electronics in the first year, when we use the biasing of the transistor or the MOSFET. In case of the MOSFET, we use VDD, and in case of transistor, that is bipolar transistor, we'll use VCC. So this is your AND gate IC. Pin number 1, 2 are input, 3 is output, pin number 4, 5 are input, 6 is output. So like this, these are the type of ICs we are using in the laboratory. Now move to the start of the evolution of digital ICs. The first was the diode logic. It was pretty much simplest, as you have seen diode as a switch. The gate is also a switch. So diode logic, it is the simplest, does not scale, and not gate, not possible, need an active element. This was the AND gate constructed with the help of the diodes. Then it was the register transistor logic. You need not bother about the circuit diagram, because you are not going to draw or design a logic a gate with the help of logic family, but you have to remember the what type of the logic ICs are there and what are their characteristics. So I have taken some examples with the circuit diagram, that how it looks. With the diode logic, we have AND gate, that is a basic gate. In RTL, register transistor logic, it replaces diode switch with a transistor switch, can be cascaded, and large power drawn. So the drawback is that it consumes more power. So the basic gate of the RTL was the NAND gate, and this is the circuit how it looks like. This much portion you have studied in transistor biasing. So typically when we cascade it with another diode, so it will be a 2-input NAND gate. Then DTL, diode transistor logic, essentially diode logic with transistor amplification. It reduced power means power consumption is less as compared to the previous two technology, and faster than RTL. The speed is fast. So again, the basic gate is an AND gate, and it looks like this. Then logic family, voltage level. What type of voltage level we consider in the logic family? And the first is VOH, output high voltage. That is the minimum voltage level at an output in the logical one state under defined load conditions. Means when the logic output of the gate is 1, then which is the minimum voltage? Suppose I am saying that I am using a 5 volt power supply, then 0 is 0 volt and 5 is the 1 volt. 1 is the 5 volt. So how much up to how much voltage it will consider it as 1 is known as VOL. Suppose I say that from 4 volt to the 5 volt it will consider as 1, and from 0 volt to 1 volt it will consider as 0. So this is the then the 4 volt is your VOH, output high. VOL, that is a maximum voltage level at an output in the logical 0 state under defined logic conditions. Just like 1 volt, it will consider 0 volt as 0 and 1 volt as 0. VIH, input high, the minimum voltage required at an input to be considered at logic 1, that is VIH. VIL, that is the maximum voltage required at an input that still will be recognized as 0 logical state. So here you can see I have cascaded some inverters. Whenever the output of this inverter is 1, then this 1 is fed to the next inverter, that is NOT gate. It will be considered at VIH because it is now input. When input is high of the NOT gate, suppose 1, then the output will be 0. Then it is known as VOL. Now when this VOL is next fed to another inverter or NOT gate, it will be considered as input low. So these are the terminologies for the voltage level in the logic families. Now the current requirement in the logic family, we have IOH, same way, current flowing into an output in the logic 1 state under specified load condition. IOL, current flowing into an output in the logic 0 state under specified load conditions. IIH, current flowing into an input with a specified high level is applied to the input. And IIL, current flowing into an input when a specified low level is applied to the input of the logic gate. So here is the same assumptions. Whenever output is high, then the current flowing is IOH. When the input is high, current is IH. When output is low, current is IOL. When the input is low, current is IIL. So these are the current requirements for the logic families. We are just taking an overview what are the terminologies on which basis the logic gates are characterized. The fan out, maximum number of logic inputs that an output can drive reliably without any breakdown. So here are an inverter driving 1, 2, 3, 4, 5 inverters. So we can say that the fan out is 5. A DC fan out equals to minimum of IOH upon IIH or IOL upon IIL. So depending upon the current, we'll find out the fan out of an logic gate so that it can drive more number of logic gates without deteriorating its performance. Propagation delay in the logic gates. Suppose we have an AND gate, that when input is here 0, it goes to 1, and here input goes to 0. So this is your first one input is VDD again, so second input will decide, and the output again goes, because we have seen a clock 0 and 1, we always delay the transition level. So the transition between when input is going from 0 to 1, from 50% to the 50% of when output going from 1 to 0. So the difference with time taken between 50% is known as propagation delay. Tau, propagation delay, PD, from high to low. Output is coming from high to low. Here is the propagation delay when PD, output is going from low to high. Tau PD L to H. In this case, here we have changed the input. but this much of time it will take to rise from 0 to 1. And another term is rise time and the proper rise time and the fall time. Whenever output going from 10% of low voltage to the 90%, then it is called as rise time. And when it comes from time taken to output come from 90% to 10%, it is known as fall time. So the propagation delay low to high, input to output propagation delay from high to low output, and propagation delay low to high, input to output propagation delay from low to high output. Speed power product, we have propagation delay multiplied by the average power consumed by the gate. This will decide the cost of your logic family. The noise margin we have here, this is VOH, this is VOL, VIH and VIL, and this term is your transition period. So the noise margin is between these two boundaries at high level and between these two boundaries at the low level. So this is the noise margin. So high noise margin high is VOH min minus VIH min. Noise margin low is VIL max minus VOL max, and we find out the noise margin of the device as minimum of VNH and VNL. So this is how we find out the noise margin of a logic family. Now come to the different type of logic family. First is TTL. TTL is bipolar transistor logic, introduced in 1964. Has shaped digital technology in many ways. Sorry. The standard family is 7400. So whatever IC number is starting from 74, you can directly say it is a TTL logic family. And nowadays it is just obsoleted. A newer TTL family is still used, that is 74ALS. LS stands for low Schottky. You have studied Schottky diodes. So these are the this is the way the which family is using 74 starting. That means you are using TTL logic family. A stands for advanced low Schottky. 00 will decide the whichever gate is there. So the first two digit decides the logic family. So this is a type of 2 input NAND gate. You need not to bother about the circuit. The distinct features of the TTL family: multi-emitter transistor, two-term pole transistor arrangement. Open LT spice example is TTL NAND gate. So the basic gate is your NAND gate. Now the evolution of TTL Schottky series LS. A major slowdown factor in the BJT is due to transistors going in and out of saturation. So when we are using Schottky diode or Schottky transistors, it will speed up or it will fast up the processing speed of the transistor. Always you see that what is the frequency of your processor, and that is frequency is nothing but the time taken to execute an instruction. So the Schottky series is TTL. Schottky diode, as we know, has a lower forward bias potential, 0.25, as in case of silicon we have 0.7, and in case of germanium we have 0.3 volt. So Schottky diode has a lower potential barrier, that is around 0.25 volt. When we have base collector junction would become forward bias, the Schottky diode bypasses the current, preventing that transistor from going into saturation, and this is your Schottky diode, Schottky transistor. These are the some TTL family evolutions. So we have 74 series, bipolar, saturated BJT, practically obsoleted, don't use in new design. Then 74S series, bipolar, deep saturation prevented by sorry, base collector Schottky diode, reduced storage time delay, and practically obsoleted. Then we have 74LS series, bipolar, low power, slower speed version of 74S series. 74AS is again improved in speed and power dissipation, relatively popular, faster TTL 74 ALS, innovation in IC design and fabrication in speed and power dissipation. 74 F series, innovations in IC design and fabrication. It is also popular. So whatever is popular is currently used. So legacy started with 74 series, don't use in new design, that is obsoleted. And we are using, widely used today is 74 AS, 74 ALS and 74 F series. Next is the ECL, emitter coupled logic. The pros are fastest logic family available with a size of 1 nano, with a time delay of 1 nanosecond. Cons, disadvantages, low noise margin and high power dissipation. Operated in emitter coupled geometry, transistors are biased and operated near the operating point, Q point. Logic levels, for 0 it uses minus 1.7 volt and for 1 it uses minus 0.8 volt. Such strength logic level require extra effort when interfacing to TTL and CMOS logic families. So the drawback is it is tough to interface between ECL to the other logic family. An open example is ECL inverter. So the NOT gate is the basic gate of ECL family. Now comes the CMOS, which you are using, which we are using widely in current scenario, current technology, as you have studied in your first year electronic circuits. It is complementary metal oxide semiconductor transistors, and other variants are NMOS and PMOS, which are almost obsoleted in digital design. It has very low static power consumption, scaling capability, large integration, almost devices means we have more number of transistors when we are using MOS as compared to TTL on a single IC. We get full swing, means 0 means 0, 1 means 5 volt, like this. Things to watch out for, don't leave input floating, susceptible to electrostatic damage. And open examples of CMOS are NOT and NET gate. Power requirements, TTL power essentially constant. In CMOS, power dependent on frequency. When we are using high frequency 3 gigahertz, 4 gigahertz, as the frequency increases, power increases in CMOS. So in the CMOS, power is calculated as FCV square. So F is frequency, C is the effective capacitance, and V is the power supply. Suppose we are using a 5 volt power supply, then it is 5 square. At high frequency, CMOS dissipates more power than TTL. Overall advantage is still for CMOS, even for very fast chips. Only a relatively small portion of complicated circuitry operates at high frequencies. So here are the series. CMOS family starts from 400. 74C is again CMOS. 74HS CMOS, a drastic increase in speed. 74AC ACT. 74AHC BiCMOS and 74LVC. These are the different logic families for the CMOS. And the trends are a reduction of dynamic losses through successively decreasing power supply. Now currently power supply is we are using in CMOS is 1.8 volt for 1 and 0 for ground. Power reduction is one of the keys to progressive growth of integration. These are obsoleted. 740 and 74C. Now take a quick look on the overview. We have different logic families. From here you can find out which is fast, which is slow, which consumes more power, and which has the more noise margin. So we should have a noise margin at the high side. The propagation delay should be minimized. So you can see the propagation delay is minimum in ECL 1.45 nanosecond. That is, it means it is the fastest logic family. When we are talking the noise margin will be better in here it is 1.5. So again 1.45, that is the 7400, that is CMOS. So CMOS provides more noise immunity. and the fastest logic family is ECL. These are the TTL, these are the CMOS. So here is the more comparison. The basic gate of CMOS is NAND NOR, for TTL is NAND, ECL is OR and NOR. Fan out is highest in CMOS. Power per gate is again low in CMOS. Noise immunity excellent in CMOS, and propagation delay is best in ECL. And this is the life cycle you can see. This is your CMOS logic family, and you can see this is the life cycle of any technology. That bipolar from the triangle, bipolar is almost obsoleted. CMOS is at its peak value, that is maturity. BiCMOS is coming into the maturity, and other devices has been obsoleted. So these are the technologies which we are using in the current scenario in the digital evolution.